In this recording, we will learn how to solve differential equations using Euler formulas that we saw last time. So recall that Euler's formula said the following. If we have e to the power a plus bi, then this can be written as e to the a cosine b plus I e to the a sine b. And if we have a minus in front of bi, then we change this into a minus sign. These are the two formulas we will need in this lecture. So now let's go back to solving second order differential equations. We consider ODE of the form ay double prime plus by prime plus cy equals 0. As usual, where a, b, c are constants and a is different from 0. Of course, we always want a to be different from 0, otherwise the second derivative will disappear. So as before, we look for solution of the form y equals e to the rx. And then we have the characteristic equation. A r squared plus br plus c equals 0. We need to solve this quadratic equation. For this topic, we assume that the equation has complex root. So how can this happen? Well, we use quadratic formula, which says that r equal to minus b plus or minus square root of b squared minus 4ac or divided by 2a. And in this case, the discriminant b squared minus ac is a negative number. And because we're taking square root of a negative number, we will have a complex number. We will have I. So say we simplify this and we rewrite the root as say alpha plus minus beta I. Okay, so we simplify and rewrite the root in the standard form of complex number. Then, so knowing R like this, complex value, then we get solutions to our ODE. Normally, we would have y1 to be e to the r1x. And let me take r1 to be alpha plus beta I. Then we would have alpha plus beta I times x And similarly, y2 is e to the, but this time we have alpha minus beta I x. However, these two solutions are complex solutions. It involves I. This will not be very convenient for us. So we will try to simplify somehow to get real solutions instead of complex solution. Because of that purpose, we're not going to use this complex solution as y1. So instead, I will label it as y1 tilde, y2 tilde here. Later on, y1, the real y1 and y2 will be different. But for now, let's go ahead with these two formulas. Then the general solution has the form y equal to, again, we're going to use c1 tilde, y1 tilde, which is e to the alpha plus beta ix plus c2 tilde e to the alpha minus beta ix. We do some algebra here. We distribute the x in. We get e to the alpha x plus beta ix. Everything here is in the exponent, plus c2 tilde e to the alpha x minus beta ix. Now we're going to use Euler formula to rewrite the exponential as sine cosine. To look at this piece, it is of the form e to the capital A plus bi. So we can use this formula. We rewrite as e to the alpha x cosine beta x, and because we have a plus sign here, it's going to be plus I e to the alpha x sine of beta x. Now be careful when we convert from complex exponent to sine cosine. We always have real in the exponent, e to the alpha x, e to the alpha x here, and then real in the trigonometric function cosine beta x. There's no I here. And sine of beta x, there's no I. The I is in this, is outside. Similarly, for the second piece, we have e to the alpha x and cosine beta x. But because of minus sign, we have minus here, I e to the alpha x sine of beta x. More algebra. Distribute the c1 tilde inside. We have c1 tilde e to the alpha x cosine beta x plus I c1 tilde e to the alpha x sine beta x plus c2 tilde e to the alpha x cosine beta x and minus I c2 tilde e to the alpha x sine beta x. The reason that I'm doing this algebra is to simplify, to get a better way to represent the solution. And here is the way to do. Look at these two terms. They have the common factor e to the alpha x cosine beta x. So I can collect like terms by combining the coefficients. I'm combining c1 tilde plus c2 tilde e to the alpha x cosine beta x plus I have these two also common factor. I is another common factor in these two, but I'm not gonna factor I because I will combine it as a new constant later on. We will see that. So I just factor e to the alpha x sine beta x. And for the constant, I have I c1 tilde minus I c2 tilde. The whole purpose is I can recognize this c1 tilde plus c2 tilde as a new constant and I label it as c1. And the whole thing here involving I c1 tilde minus I c2 tilde, I recognize it as a new constant denoted by c2. So I may rewrite out my solution as c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x. So suddenly, by renaming the constant, the complex imaginary unit I disappear, and now we have a more familiar format: c1y1 plus c2y2. As a result, for the complex root, this is our y1, and this is our y2. So instead of using the complex solution like above, like this, exponential with complex number, we use real solutions involving exponential and trigonometric functions. So you have seen the algebra here, but you don't need to redo it. So to summarize, if we have complex root or by using quadratic formula and we have alpha plus minus beta I, then you may write down right away what real y1 and y2 are. y1, for the piece with the I, we get exponential e to the alpha x, e to the alpha x. But for the piece with I here, the coefficient in front of I, we will have trigonometric function. We begin with cosine beta x, and here the second one will be sine of beta x. So these are the two solutions. And if you take the ratio y2 divided by y1, the exponential cancel out, and we have sine beta x over cosine beta x, which is tangent of beta x. And it's not a constant, so y1 and y2 are linearly independent. Because of that reason, the general solution to our ODE is y equal to c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x, as we saw earlier. Now, let's look at a few examples how to use the formula. The first example, solve the initial value problem. Two y double prime plus 2y prime plus 5y equals 0. As usual, this is our ODE, and we have initial conditions, y at 0 equal to minus 1, and y prime at 0 equal to 2. So you may pause the video here and try yourself. So as before, we have the characteristic equation. Two r squared plus 2r plus 5 equals 0. To solve this equation, you won't be able to factor. Instead, you could use quadratic formula, or you could complete the square as well. That's another method to solve. Let's use quadratic formula. We have minus b, which is 2 here, plus or minus square root of b squared minus 4ac all divided by 2a. So we get minus 2 plus or minus square root of 4 minus, this would be 40, all divided by 4. So r is minus 2 plus or minus square root of negative 36 over 4. So how do we simplify this? We need to rewrite in the standard form for complex number. So first, square root of negative 36. Because it is a square root of negative number, we will have imaginary unit. As before, let me just remind you, split it into square root of 36 times square root of negative 1. And this is I. And we know that square root of 36 is and all divided by 4. So we simplify as minus 2 plus or minus square root of 36 I over 4. But we need to rewrite in standard form. So minus half over 2 plus or minus 2 over 4 minus 6i over 4. Keep in mind, we need to split by dividing each terms in the numerator by the denominator. And so we get minus a half plus or minus 3/2 I. We have complex root of the characteristic equation. Using the above formula, we may write down y1 and y2. How do we do that? You may go back and look at the formula, but here is how. For part without I, we will have exponential. So we get e to the minus a half x, e to the minus a half x. But we need to multiply by the trigonometric function. Plus or minus the number in front of I is 3/2. So we will have the first one is cosine 3/2 x. And the second one is sine 3/2 x. These are the two real solutions. And then The general solution is y equal to c1 e to the minus a half x cosine 3 half x plus c2 e to the minus a half x sine 3 half x. Now we need to use initial conditions. Let's go back to initial conditions. We have two of them. The first one is here, which says that when x equals 0, y equal to -1. X equals 0, y equal to -1. We plug this value in the formula. So y equals 1 and x equals 0. So we have c1 e to the 0 cosine of 0 plus c2 e to the 0 and sine of 0. Simplify this. We have -1, c1 e to the 0 is 1, cosine of 0 is also 1, so c1 plus c2 e to the 0 is 1, but sine of 0 is 0, so it's just gone. Then we have the value of c1 very easily. The c1 equal to -1. This is the first value for the constant. Now we're gonna use the second initial condition, x equals 0, and let's go back here. It says that when x equals 0, the derivative is 2. Y prime equal to 2. So as before, in order to use this initial condition, we need to compute the derivative from the general solution. We have the derivative of this. C1 and C2 are constant. But for this part, we need to use product rule and the Sampson product rule for that. And because C1 is a constant, I will just write like this. C1 times, and the product rule comes in here, plus C2 times, and again product rule inside. In fact, we need to use both product rule and chain rule. You should pause the video and try the derivative yourself. But for the product rule, we take the derivative of the first one, we get e to the minus a half x times minus a half. Or we could rewrite as minus a half e to the minus a half x, and then we have cosine of 3 half x. For the second one, for the second part of the product rule, we keep e to the minus a half x as it is and take the derivative cosine of 3 half x, which gives us minus sine of 3 half x times 3 half. So we would have minus e to the minus a half x, and then sine of 3 half x. But remember, we have a number 3 as well. So 3 half outside there. Similarly, we have to use product rule for the second part here. So we get minus a half e to the minus a half x sine 3 half x plus e to the minus a half x. The derivative of sine is cosine. We have cosine of 3 half x. But again, don't forget we have 3 half because of the chain rule. The derivative is a little more difficult, and involved, and it's involved several terms, so you need to be careful. Now let's plug x equals 0 and y prime equal to 2. We have 2 for y prime and then c1. Now when x equals 0, we have here minus a half e to the 0 cosine 0, and then minus e to the 0 sine 0, and then we have 3 half here, plus c2 minus a half e to the 0 sine 0, and plus e to the 0 cosine 0 times 3 half. Don't forget that. So several things cancel out. Sine 0 is 0, so cancel this, cancel. We may simplify it as 2 equal to c1 times minus a half e to 0 is 1, cosine 0 is also 1, so we just have minus a half plus c2 times e to 0 is 1, cosine 0 is 1, so we have 3 half here. Now before we continue, I just wanted to mention that in my experience teaching the class several semester, some people just kind of like sloppy when they saw a sign that just crosses out, sign crosses out. That is not correct. You cannot cross out the terms in the derivative. You can only cross out after you have plugged x equals 0 in. Okay, so don't be sloppy. You need to rewrite the step clearly like this and just cross out whenever you see side of 0, which is 0. So we have 2 equal minus a half c1 plus 3 half c2. Recall what is c1 we have found earlier. C1 is negative 1. So minus a half negative 1 plus 3 half c2. So we have 2 equal to a half plus 3 half c2, and you need to solve a c2. You may try yourself, but I believe c2 is 1. So knowing c1 and c2, we have our answer. Y equal to c1, which is minus 1. Go back here. c1 is minus 1 e to the minus a half x cosine 3x, and c2 is 1. So we get minus e to the minus a half x cosine 3 half x plus c2 is 1, so e to the minus a half x and sine 3 half x. This is the answer, the solution to our initial value problem. Now you have the example, but you may wonder, would it happen in real life that we need complex number? It turns out that it does happen in real life, and actually it's happened with a very familiar example. Let's look at example 2 here. We consider a spring mass system. So imagine like this. We have a spring attached to something, and there is a mass, an object. This is the equilibrium point, so it's at rest, and we label it as 0. This is at rest. Now suppose that we pull the mass away a little bit. To a certain position here. Say 1 unit. We could be using say centimeters or inches or whatever one, but unit. This is at time t equals 0. We put and we let it go. Then what happens? Everyone would imagine that the mass oscillate, right? So at a certain time t, at a certain time t, the mass will be somewhere in between 0 and 1. T positive here. Now we wanted to describe the motion of the mass. More specifically, we want to find the formula for the position of the mass at time t. Oh, here at time t, we have a certain position. Let us denote that position. Usually for horizontal, we will use x, but because in the previous example, we use x for the independent variables. So I don't want to use x. Instead, I will use, say, y. Y of t is the position of the mass at time t. So let yt or just y, but we know that y is a function of t, be the position of the mass at time t. We want to find out the formula for y of t. Now before doing that, let's look at the initial values. At time t equal to 0, right here, the position is at 1 unit. So at t equals 0, we have y0 equal to 1. But what is y prime is 0? Y is a position, so y prime represents the velocity. But what happens is that at time t equals 0, we just pull the mass a little bit and let it go. So there is no velocity at the beginning. That's why velocity y prime is 0 is 0. This is the initial condition. But of course, in order to determine the formula for y of t, we need to know the differential equations. How do we determine the differential equation? Well, you get it right. we need to use Newton's second law. What are the forces acting on the mass here at any time t? There will be several forces, but we are interested in forces in the direction of motion. So for example, there is gravity, but we won't care about gravity because it will not affect the motion. So first we have the force from the spring. The spring's force. And there may be friction as well. But for simplicity, in this example, assume no friction. So assume friction is negligible, no friction. So we only have the spring force. But what is the formula for the spring force? First of all, it's in the reverse direction of motion, so it's minus from what law in physics that you have seen, minus k times the displacement, which is y. Maybe in physics you use x, but again, we are using y for our displacement. This is called the Hooke's law. That is spring force. And K is the stiffness of the spring, a spring constant, where K is the spring constant. So now let's use Newton's second law. Because we don't have friction, essentially it's just one force acting on the object. Newton's second law says we have ma equal to F. Ma is acceleration. What is the relation between acceleration and the displacement? Acceleration is the derivative of velocity, right? And velocity is the derivative of the displacement. So we have m times y double prime. And F, as above, is minus ky. Minus ky. Let us rewrite here minus ky. So I'm gonna rewrite the equation by bringing this term to the left side. We have my double prime plus ky equals 0. Recall that m and k are constant. M is the mass of the object, and k is a spring constant, the constant. Only the unknown function is y. So what is the characteristic equation? For our ODE above, this is m r squared k times 1, because y, there's no derivative here, so it's just 1 when we rewrite the characteristic equation for 0. So what do we get? We solve for r. You may use a quadratic formula by rewriting r squared plus 0r plus k equals 0. But it's easier to just solve r squared. We have r squared, mr squared is minus k. So r squared is minus k over m. And then we take the square root, be plus or minus square root of minus k over m. But of course, m and k are positive constant, so minus k over m would be a negative number. So we split into plus or minus square root of k over m, square root of minus 1, and so our values for r are complex number, plus or minus square root of k over m times I here. This is complex root. Alright, so we have solved for r and we get two complex root. In order to write out the solution, we need to rewrite in the form of alpha plus or minus beta I. But in this case, alpha is 0 and beta is square root of k over m. So from here, we have our y1. Because alpha is 0, there's no exponential. We only have cosine and sine here. Cosine of square root of k over m t. Because our independent variable is time t, we need to use t. And cosine y2 is sine of square root of k over m t. And the general solution is y equal to c1 cosine square root of k over m t plus c2 sine square root of k over m t. And now we use initial condition. When t equals 0, y equal to, let's go back here. When t equals 0, y equal to 1. Plug these values in. We have 1 equal to c1 cosine of t equals 0. So it's 0 plus c2 sine of 0. And we cancel this. Cosine of 0 is 1. So from here we get c1 equal to 1. Now next we need to use the second initial condition, which says that when t equals 0, y prime equals to 0. Right here. When t equals 0, y prime is 0. So to use this, we need to take the derivative of the general solution. Take the derivative of the entire general solution right here using the chain rule. We have y prime is c1. Now this time we don't have exponential, so the derivative is easier. Derivative cosine of this will be minus sine. I put the minus in front. Minus sine square root of k over m t. But don't forget we need to multiply by square root of k over m. That's from the chain rule. And then c2 times the derivative of sine, which is cosine. cosine of square root of k over mt, and again we need to multiply by square root of k over m by the chain rule. Now plug t equals 0 and y prime equals 0. We have 0 equal to minus c1 sine of 0 square root of k over m plus c2 cosine of 0 square root of k over m. And simplify. This is sine of 0, 0. Cosine of 0 is 1. So we have c2 times 1 times square root of k over. But then we solve for c2. We get 0 divided by whatever here. So c2 equals 0. So finally, we have the answer y equal to c1, but c1 is just 1. So c1 cosine square root of k over m times t, and plus c2, but c2 is 0. Plus c2 times sine, but c2 is 0, so we don't have the second part. And this is the solution. So what it means is that for our spring mass system without friction, if we just pull the mass away and let it go with no initial velocity, then the mass oscillates according to the function cosine. And this is the end of the lecture for this topic.